In our previous set of tests, our data was compromised due to the slider causing a friction barrier we couldn't get over. To overcome this problem, we simply angled the apparatus so that it would face upwards. Now the force sensor would measure the thrust in addition to gravity, reducing the amount of data lost to friction. There we go. Though the setup did work, and we recorded data, having this particular test be one that created sparks made the setup less than safe. Like a Roman candle, the small nozzle fired up tons of particles of molten polyethylene and later ablated steel a couple dozen feet into the air. On the positive side, we did collect records for the flight, and the results are astounding. Test firing 10 had an average thrust of 3.5 newtons and an average exhaust velocity of just over a kilometer per second. Without a doubt, we can affirm that the gases are being expelled at supersonic speeds. However, it is unsure if this boost was caused by the convergent-divergent nozzle, the increase of air pressure up to 80 psi, or a combination of the two. We were able to calculate these values through the application of conservation of momentum. Specifically, the average exhaust velocity is equal to the average force over the average mass flow rate. We find the average force by measuring the force of the rocket over time and finding the average of that through a Riemann approximation. We find the total mass flow by measuring the mass of the fuel rod before and after the firing, and using mole fractions to calculate the mass of the oxygen lost too. All of these figures are included in the firing specifications. However, this engine was inherently unsafe, and the heat managed to melt the side of the nozzle, adding it to the collection of destroyed nozzles we have. For the larger one, we realized that we couldn't fire upwards again due to the safety risks, but we wanted to make sure that we could still collect data. We decided to position the engine sideways, but with a slightly upwards tilt, and hope that friction wouldn't ruin the results. Stable. Test firing 11 went beautifully, and we observed similar results to the last test too. Test 11 had an even higher average thrust and a calculated exhaust velocity close enough to the last test to be within the margin of error. The first video of the test had lower resolution because we chose to lower the exposure on the camera in order to better see any shock diamonds if they existed. Another important observation is that the exhaust didn't fully expand to the shape of the nozzle, which is contrary to what we observed in Test 8. This leads to a comparison of the two nozzles. Through our experimentation, we believe that the ideal nozzle for this rocket exists somewhere between the two we have, but overall, the larger nozzle performed better. It is likely that the overwhelming heat that destroyed a couple of our nozzles came from nozzle throats that are too tight. The point of a throat in a rocket nozzle is to get the exhaust to choke, which is when it accelerates to the speed of sound and cannot be accelerated any further due to constriction. If the nozzle constricts further, rather than accelerating, the gas compresses, and that induces compressive heating, which is likely the source of all the melting that has compromised a lot of our nozzles. In contrast, it seems the larger nozzle choked the gas even with a throat with 4 times the area of that of the smaller one. A couple of mysteries still remain. At this time, we don't know exactly why the exhaust flame doesn't follow the nozzle. It tends to just fire in any direction it wants, sometimes even burning through the wall of the nozzle to do so. We also don't know what the upper limit to applying pressure to the oxygen is. Eventually, we should be pushing so much oxygen through the engine that it will just leave the system without combusting, but we don't know how far that is. There are also a bunch of one-off anomalies, such as what the blue flames were, or why that particular test generated so much heat. But in general, we can answer them with bad craftsmanship. The hole in the fuel rod is misaligned, the fuel rod isn't perfectly flushed with the walls of the engine, and the things are held together with non-airtight screws. We are approaching the limits of what a backyard hybrid rocket can accomplish. From here, the only way to improve is to incorporate highly precise and expensive aerospace engineering techniques into the engine. We might return to this, or we could pick up a different type of engine entirely.